Continuing on Physical Chemistry, Chapter 2, we're now beginning Section 2. We're going to talk about PV work, pressure times volume work. First, let's refresh our memory. We just did mechanical work in the previous section. The differential of work is equal to the x component of force times the displacement in x. This is for one dimension, obviously. Now remember, the differential of work is greater than 0 if the x component of force and the displacement in x are in the same direction. Now, the differential of work is less than 0 if the x component of force times the displacement in the x are in opposite directions. Now, first let's talk about reversible PV work. Now, let's look at a piston here. So this is the cylinder. Here's our piston. We've got pressure pushing down on it. We're going to say this bottom position here, this is B, just arbitrarily calling it lowercase b so we have a reference. That's the fixed end of the position. This is not going to move. Now our distance of the piston to the bottom of the cylinder, we're going to call that L. Just lowercase cursive L for no reason except that we need some sort of reference. Now we're going to say the positive x direction is down this way. So if that confuses you because you're looking at sideways or something, well, you just got to get used to it. You can call it P or W or whatever, but we're going with x. So remember, we said pressure is force over area. We're only moving in one dimension here. We're looking at one-dimensional movement, so it's really the x component of the force divided by the area. So again, capital A is the cross-sectional area of the piston. Doesn't even matter what shape it is. It could be rectangular or octagonal or whatever. Octagonal, how do you say that? Circle is most practical. I think in real life they're all circular, but it doesn't matter. So again, lowercase b is the fixed end of the position. So at any time, x is the current location, the current of the piston in the x-axis. So the length here, or the height of the piston, whatever you want to call that, that's going to be just b minus x. So remember, the differential of work is going to be the x component of the force times the differential in x. It's going to be pressure times area. Remember, we substituted in, we solved for f of x equal pressure times area times the differential of x. Now we also know the area here, remember this, the cross-sectional area of the piston, is going to be the volume divided by the length. So anyway, capital V is volume. Now it's going to be minus. We'll explain why in a bit. We're doing differentials. So it's going to be minus the change in volume. See, if it's volume divided by x, it'll also be the differential of volume in x. That's kind of weird. Now remember, so by our nomenclature here, dW, the differential of work, is the work done by the surroundings, or the work done on the system. So positive work means energy coming into the system. Negative work means energy going out of the system. That way it matches all the other stuff. Positive means coming in, minus means it's leaving. Now volume is equal to the area times the length. So the volume of the piston here is equal to the area of the piston times whatever height of the piston. So that's also going to be substituting in length is b minus x. So we have the volume as area times b minus x. And then distributing, we get volume is equal to ab minus ax. So we want to take the differential of v, the differential of the volume. Okay, so that's going to be differential of volume is equal to the differential of AB minus the differential of AX. Now remember, A, the area is constant. The piston's not going to get any wider or longer. And the B is constant. That's the fixed end. So, if A and B are both constant, this differential is 0. If A is constant, you could pull it out of the differential. So the differential of the volume is equal to just minus area times the displacement in x. So solving for A, we get A is equal minus the derivative of volume with respect to x. That's what I was trying to explain up here. I probably should have done this first and then did it, so you understand why. So the derivative or the differential of work is equal to pressure, substituting that back in, minus the differential of volume with respect to x times the differential of x. So the differential of x is going to cancel out. So we just end up with minus pressure times the differential of volume. So we get the differential of work is equal to minus PdV for a reversible process. And this is PV work only, of course. Now, continuing on Chapter 2, Section 2, we're still talking about a reversible process. It's important to realize that a reversible process is theoretical. It can't actually happen in real life. It doesn't exist. It's a tool we're using to learn. The maximum work out of a system is from a reversible process. Now, we're not going to really prove that for about 5 more chapters, but take my word for it for now. It takes infinite amount of time. You see, the reason is you have to go really, really, really slow so that you're always at equilibrium, basically. And again, it's calculus. Excuse me. It happens in infinitesimal steps. That's one of the reasons it can't happen in real life, because in real life we have atoms and molecules and they're all finite. So the reason we have to go infinitely slow and so on is because we're always infinitely close to equilibrium. But what's important, remember, we call it a reversible process for a reason. Because at any time, you can just reverse and go back the other way, which is kind of what makes it obvious that it doesn't happen in real life. So we already said the differential of reversible work is equal to minus the pressure times the differential of volume. Now this is true, we didn't really specify it before, but it's only for a closed system. If air or whatever can leak in and out of your system, it's going to be different. It's only true for a reversible process, but it doesn't matter what shape of the container. You can still figure out the cross-sectional area and so on, and it should work out exactly the same. It's just your math is going to be a little bit different to come up with how you did it. Now, I already mentioned this before, our conventions. So the differential of volume is less than 0, means our system is getting smaller, so it's being compressed. Well, then the reversible work has to be greater than 0. Because to compress our system, we have to do work on the system. So the final volume minus the initial volume is going to be negative, since our system shrank. We compressed it smaller. Now, on the other hand, if the differential of volume is greater than 0, our system is expanding. We call that expansion. Then the reversible work has to be less than 0. The reason is, by allowing the system to expand, we're doing work by the system. We're using energy in the system and we're doing work on the surroundings. So the final volume minus the initial volume is going to be positive because our system expanded. It grew. Now, so this also gives us in integral form, the integral from state 1 to 2 of the differential of reversible work then is going to be the integral from state 1 to 2 of minus P with respect to volume. That's pressure and volume. So work reversible, so the integral from state 1 to state 2 of the differential reversible work, that's just the reversible work. So our reversible work is the integral from state 1 to state 2 of pressure with respect to volume. And this is true whether the pressure is constant or not. Now pressure is a function. Remember we talked before about how a variable can be considered a function of other variables. So here we're saying pressure, we're going to consider it a function of the volume of the system and the temperature of the system. What that means is it's a line integral, which means it's path dependent. So here's an example. We've graphed pressure against volume here. And let's say that our initial pressure is way up here and our initial pressure is down here. So we're squeezing our system. The pressure is going down. Actually, our system is expanding. Duh. So this shaded area under the curve, that's the integral. That integral is the work. So when you need to find out the work done on the system or by the system or whatever, you're going to have to figure out not just your initial and final, but how it gets from here to there, so you can integrate and find that area. And then you'll know the work. Okay, we're chapter 2, we're still in section 2. So here's another example. This is pressure versus volume. This is supposed to show that we have the exact same initial and final states, but this time we're going constant volume and then constant pressure. The work is still the shaded volume. Maybe I'll put these together. Oops. You can see I didn't really draw it to the same scale, but the area here is less than the area here, even though you have the exact same starting position and the exact same ending position. Here's a third choice out of infinite choices. So here's pressure versus volume still. We still have our same initial pressure and volume, our final pressure and volume down here. This time we're going constant pressure and then constant volume. And again, the work is the area under the curve. And as you can see, it's a lot bigger than that. It's even bigger than the one we did before. So that's why it's important to remember that when you're doing work, you have to know exactly how it was done, not just your initial and final. We got away with initial and final before because it was a one particle system. That was a little bit different. Now we're talking about gases. So when we have, this doesn't really show it yet, but when we have more steps, we get more efficient. If we have infinite steps, it's the most efficient. That's why with a reversible process, we get the most amount of work. Now there are two types of work. There's reversible and irreversible. Reversible work, we already showed you, at least when you're talking about gases, is minus the integral from state 1 to state 2 of pressure with respect to volume. Irreversible work, we're abbreviating IRREV for irreversible. We can't actually calculate that. We don't have a way to do it. At least not in thermodynamics. Maybe somebody else has figured it out, but not me. So here's our system. Remember the nomenclature that we're using, the standard we're using. If any energy is coming to the system, no matter how it's coming in, we consider that positive energy. And if any energy is leaving our system, no matter how it leaves, such as work is a type of energy transfer, then that's minus energy. So that's why we say that positive work is done on the system and negative work is done by the system. Okay, that is the end of chapter 2, section 2.